Exercise 229 is asking you to draw the resonance structure of a certain compound that you can get from the fruit of this Acatea corymbosa plant, which is a native plant of the Brazilian Cerrado. So these fruits here have this molecule jiggling around in them, among a million other molecules, but they have this special molecule jiggling around in them. And for our purposes, we just want to draw the resonance structure of this. So when you see a molecule that you've never seen before, you would just go methodically through it and see if it has any of these resonance patterns. And one thing you want to do first, because it'll help you to see some of the resonance patterns, is to draw in the lone pairs. So I'm going to copy this molecule down. Notice that OH there, that's really an oxygen bonded to a hydrogen. So keep in mind, there's that bond there. Alright, so that's our molecule, and let's just go one at a time. So first, do we have an allylic lone pair? Well, first, let's draw in all the lone pairs. Notice that each of the oxygens has 2 bonds, and so 4 electrons around them. So they each need 4 more, so they each have 2 lone pairs. Okay, now they have 8 electrons around them. Okay, are either of these lone pairs allylic? The lone pairs in this top oxygen are nowhere near a double bond. If you go one atom over, this atom is not involved in a double bond. So those are not allylic. The lone pairs at the bottom left are on an atom in a double bond. They're not one atom away, so those also are not allylic. And so we do not have this top resonance pattern. We have lone pairs, but none of the lone pairs are allylic lone pairs. How about an allylic positive charge? Well, nowhere in this molecule do we have a positive charge, so we don't have that resonance pattern. How about a lone pair adjacent to a positive charge? Well, we have plenty of lone pairs, but none of them are right next to a positive charge. There's no positive charge here or here, right next to where the lone pairs are. So we don't have that pattern. How about a pi bond between 2 atoms of differing electronegativity? We have 2 pi bonds in the molecule. We have a pi bond at the bottom right. Remember, pi bonds are every bond after the first bond that you form. And then we have another pi bond over here, sort of at the bottom left. Now, this pi bond at the right is between a carbon and a carbon, and those have the same electronegativity. The electronegativity increases as you go up and to the right on the periodic table. Carbon and carbon, those are in the same place. So those have the same electronegativity. So although we have a pi bond there, it's not between atoms of differing electronegativity. So that isn't involved in resonance. How about the bottom left? Here we have a pi bond, and the pi bond is between an oxygen and a carbon. Oxygen is one of those extremely electronegative elements that you want to watch out for. And so it is much more electronegative than carbon. It's right there in the top right. In the top right, you have nitrogen, oxygen, fluorine, and chlorine. So those are really electronegative elements. All right, so we do have that 4th pattern here. Now we haven't talked about a 5th pattern, so it's not relevant. This 5th pattern here isn't relevant for this problem. Also, once you learn the 5th pattern, you can go back to this and you'll notice it's not in this molecule either. But because we have the pi bond between 2 atoms of differing electronegativity, we can draw in the curved arrows. Well, first of all, let's warn the world. This molecule has resonance, so neither of the structures we draw is going to be true. You have to take the average of the 2 in order to get the real molecule. Okay, so whenever you have a pi bond between atoms of differing electronegativity, the pi electrons go onto the more electronegative atom. So we take that molecule, and anywhere where you have the tail of a curved arrow, that's a place where electrons are moving away from, so you erase those. And anywhere where you have the head of a curved arrow is a place where electrons are moving or arriving, so you draw them in. If the head of a curved arrow points at an atom, then you draw in the electrons as a lone pair. Now you'll notice that the formal charge in this oxygen now is a -1, and the formal charge on the carbon is a +1. It's 4 minus the 3 line, so +1. And for the oxygen, it's 6 minus 6 dots in 1 line, so -1. And there it is, the two resonance structures. And the fact that there is resonance associated with this molecule means that the molecule is stable, more stable than it otherwise would be, and more rigid than it otherwise would be. And so it would behave as a better chemical messenger. Because it's more stable, it'll survive as it travels from the place that's sending the message to the place that's receiving it, and because it's rigid, it'll more reliably fit into a receptor site.